In section 3.1, we're going to think very carefully and deeply about something that maybe you've been taking for granted for years. Specifically, what does 5 mean? If you were tutoring a small child and trying to teach them about counting, what do you say about 5? It's one of those things that's so basic that it's hard to come up with a definition from scratch, right? And you might think, well, it's the number that comes after 4. And although that's a true story about 5, that doesn't really define what a 5 is, right? Or maybe you come up with this. You come up with a hand and say, well, 5 is this many. I know 5 when I see it, and 5 is this many. That is actually surprisingly close to the truth. So more generally, what does it mean to count? Here's a different example for us to look at. Which set of dots is larger, green or blue? What if I challenged you to figure out which set was larger without counting either set? Now, the definition that's relevant here is one-to-one correspondence. Two sets have a one-to-one correspondence, so either they have it or they don't. If you can draw or describe a perfect matching from the elements of one set to the elements of the other, and there can't be any leftovers. So in the case of the sets of dots, you would start matching up green dots to blue dots, and you match up all the way to the end, and no matter how you match them up, there will always be a lonely blue dot who's left out. And so these two sets do not have a one-to-one correspondence. So more generally, how does counting work? And put yourself in the shoes of, say, a 4-year-old who's going to count the dogs in this photo. You might point at the individual dogs and say the number words, right? And that's actually exactly how we want to think of counting. So you're going to attach the word 1 to one of the objects in the set. You move on to the next object in the set and you say or match the word 2 to that object. And you keep going until every object in the set has a number word attached to it. And so what we would say for this problem is that the set of dogs and the set 1, 2, 3, 4 have the same cardinality. And any set that has a one-to-one correspondence with the set 1, 2, 3, 4, we say there's 4 things in it. Now, this all seems like a little much work for something that's pretty basic, right? But what happens with infinite sets? Some pretty crazy squirrely things happen. So here are 2 infinite sets. Do they have the same cardinality? Do they have a one-to-one correspondence? And at first glance, it doesn't look like they have a one-to-one correspondence because that second set is only the evens, right? And it only has every other number from the first set. So it kind of makes sense to say, well, it looks like the second set is only half as big. But see, here's the thing. If you write down both sets in a nice vertical way like this and you start pairing elements of the sets to each other, what happens is every natural number in the top set has a buddy in the second set of even numbers, and there are no leftovers in the top or the bottom. These two sets have the same cardinality. These two sets have a one-to-one correspondence. So something I want to point out here is that you might try to make a one-to-one correspondence between two sets and it might not work out the way that you want. But just because a correspondence doesn't work out, it doesn't mean you get to stop and say there's no correspondence possible. So with the natural numbers and the even natural numbers again, maybe you thought you would pair 2 to 2 and 4 to 4 and 6 to 6, so on. And in which case, this is not a one-to-one correspondence, right? This matching doesn't work out. There's lots of leftover odd numbers on top. However, these two sets do have a one-to-one correspondence, and this is the correspondence that works. So there are all kinds of bad correspondences out there. That doesn't matter. The fact that there's one good one-to-one correspondence means you say, yes, these two sets have the same cardinality.